Young modulus. To be able to compare different materials, regardless of their dimensions, it is useful to use stress and strain rather than tension applied and extension. Stress, given the letter sigma, is the tension per unit cross-sectional area, and so has units of newtons per square metre or pascals, the same as pressure. Strain, given the symbol epsilon, is extension per unit length, which, being a length divided by a length, has no units. If we plot a stress against strain graph, we find that the stiffer the material, the steeper the gradient. So here we have a stress against strain graph. Steel has roughly twice the stiffness as brass. The gradient of a stress-strain graph is known as the Young modulus for a material, and so the steeper the gradient, the greater the Young modulus, and the stiffer the material. Young modulus is given the symbol capital E and is found from the stress divided by the strain. If a wire of cross-sectional area A and original length L is subjected to a tension T extending by a length delta L, we find that the Young modulus E is equal to the stress, tension over area, divided by the strain, change in length over original length. We can rearrange this to give Young's modulus as the tension multiplied by the length, divided by the cross-sectional area, and divided by the extension. As stress has units of pascals and strain has no units, we find that the Young modulus also has units of pascals, the same units as those of stress. Let's look at an example. A 3 mm diameter steel cable of length 44 meters supports a stationary lift of weight 9,200 newtons. Calculate the extension of the cable if the Young modulus for steel is 200 gigapascals. Well, if we first write down the Young modulus equation, then rearrange for delta L is equal to tension multiplied by length divided by Young modulus and the cross-sectional area. Then, putting in our numbers, the tension was 9,200 newtons, the length of 44 meters, the Young modulus 200 gigapascals or 10 to the 9 pascals, and the area is pi r squared, pi the radius of the wire 1.5 millimeters or 1.5 times 10 to the minus 3 meters squared. This gives an extension of 0.29 meters. To find Young modulus for a material, you would need to use a micrometer to measure the diameter of the wire in several places and take an average to calculate the cross-sectional area. You would then use something like Searle's apparatus to measure the extension of the wire. Here we have a control wire of the same diameter and material as the test wire. The control wire supports one side of a bridge on which is placed a spirit level. The control wire is kept straight by these control weights. The test wire supports the other side of the bridge, and the height of this bridge is adjustable on the test wire side by use of this micrometer. We can adjust the number of weights on the test wire and then adjust the micrometer to ensure the spirit level is level, and then read off the amount by which this side of the bridge has been raised, and therefore the extension of the test wire. We could calculate the stress and strain for several different values of test weight and plot a stress against strain graph. The gradient would give us the Young modulus.